Are you doing all three then? Yeah.
Yeah, it's screen that I had the problem with, but
Ah,
I'm taking the exam while I can.
oh, okay.
Okay, so hi, welcome back from Passover break. And we are, I'm just reminding you, we are studying linear algebra. And I will remind you in 2 seconds after I finish dealing with the screen here. I will remind you where we left off. We just started a new subject. A system of linear equations and how to solve these systems using matrices. So let's get to it. So I think this is a good place to start. And just recap. A linear system of equation is a set of a few linear equations. What are linear equations? This is the general form. Is any linear equation is a sum of coefficients, which are numbers from the field, times a variable, and the variable is just not squared, not square root, not multiplied by anything, just of the following form: number times a variable plus a number times a variable equals to a number. So I'll go back to the example like this. This is 1 times x plus 1 times y equals 3. I wish to have an example in 3D, to be honest. Let's skip to this one. 1 times x plus 1 times y plus minus 1 times z equals 1. And the second equation is 1 times x plus 0 times y plus 2 times z equals 0. And the solutions of a linear system of equations are if it's three-dimensional, the triplets x, y, z, such that when we substitute the triplets into the variables in all of the equations hold. So we're looking for the solutions, the common solution, the intersection of solutions to all equations. And how do we do it? The names of the variables are irrelevant. So we just write the coefficients in a table of numbers called a matrix. Did I speak about homogeneous system yet? No, I will mention it in a bit. And then we do elimination operations. We either add a constant time a row to another row, or we multiply a row by a constant different than 0, or we switch places between two rows, and any of these operations does not change the set of solutions to the system. And the idea behind it, and let's go back here, it's after we do these operations, we get another linear system of equation. Look, the first system holds these two equations, x plus y minus z equals 1. And after the elimination process, we get different equations. You see, the first equation is x plus 2z. That wasn't the equation from the start. And the second one is also different. However, in the final process that we will define today, we'll start with it. It's very easy to understand what are the solutions. Look here. We can choose whichever z we like, and then we'll get, according to the z, the value of x and the value of y. right? So that's the idea. Looking at the original system, we have many variables in many different equations, but after the elimination process, when we get to the echelon form, I will define it today. We get equations that you can read the solutions right off of them, and that's the idea, basically. Okay. And this is a geometric interpretation of the question, not of the answer, right? These planes are the original equations. These planes are the solutions to the original equations, and we're looking for the intersection to the points which are on both places, and we got an intersection line. These are all the points on the intersection line, and everything makes sense. Okay, so that was a recap. Do I write the number of each lecture? Do any of you remember? Sometimes I do, sometimes I don't. I do.
I think you do.
So I need to see what number lecture it is. Don't see it. I scroll a bit more.
4 people.
Nah, no, I think I'm not writing. Okay. So, we saw that the elimination process does not change. I think I can make the font a bit smaller. I think that's okay. We saw that the elimination process does not change the set of solutions. Now we will define what is the matrix form we aspire to. So first definition, a value, a place in a matrix is called I'm thinking about how to translate it. It has many names in Hebrew.
You said, is this the same as we talked last time about the first non-zero value?
Yes,
I think you wrote it.
I think it was on the Tirgul, no? I don't remember writing the first non-zero value, did I?
I remember that we got to the solution to that system of equations, and
I spoke about it, but I didn't define it yet.
it's lower, but I thought you're right.
It was bounded and unbounded variables,
Yeah.
but it has a connection to, but it's not exactly the same. No, I don't think I did in the lecture. Okay, and so a place in the matrix is called pivot. That's an English word anyway. In Hebrew, I say evar potech. That's an opening element, I don't know. So a place in a matrix is called a pivot if it is the leftmost element in its row, which is different than 0. So each row could have a pivot, unless what kind of row would not have any pivots?
That it's all 0.
Exactly. If it's all 0, then there is no pivot. Otherwise, there are pivots. And then definition, and I won't write it in the notes, but just to say what is so special about the pivots. Think of them now as coefficients of variables. If the coefficient of a variable is 0, then basically this variable does not appear in the equation. So the pivot marks the first variable that actually appears in the equation. And they are important because we want to separate the variables. So we want variables to appear in as few equation as we can. So the pivots are the way to speak about them. And that's what I'll do now. A matrix is called echelon form or in echelon form, sure, in echelon form. And I also am not sure if I'm writing echelon correctly. Let me for a second look at it.
ECHELON.
In any case, I want you to be familiar with this site as well. I don't remember if I've shown you this before, but I will write it. I will add it here. Link to a useful website. And it's also written there, the name, right? But we'll use it every now and again. System of equations calculator. That's what's relevant for now. And Gaussian elimination, that's what, oh, in it. Echelon form, yeah, it's ECH without the S. And in any case, look at it. It can help you, it can solve a system of equation. Let's look at an example we did and let it solve it. So let's look at this example. 1 times x1 plus 1 times x2, which we called y, and minus 1 here equals 1. That's the first equation. The second equation is 1, 0, 2, 1, 0, 2, 0, right? Yes. And I will tell him solve. What is the solution that it finds? Look at this. So x3 is RZ. We switched his name to T. We like to substitute a parameter in it. And what is the solution? We got minus 2 times T, 1 plus 3 times T, and T. Exactly what we got. So that will help you. Okay. If you only use this calculator to solve your problems, then when the test comes, you will not succeed because it takes practice. However, I think it's a very good idea to do it by yourself and then use the calculator to make sure what you did is correct. And if you can see, it really explain the different steps and it's very helpful. For now, I mostly open it to find how to write the echelon form, actually row echelon form. So I'll use this name. It's called in row echelon form because we're working on the rows. If two conditions must hold. If there are any lines of only zeros, they should be at the bottom. That does not really matter, but that's part of the definition. Why doesn't it really matter? Because when we do the Gauss elimination process, we have the ability to change the location of rows, right? So it's really easy to change the locations of 0 rows to the bottom. And the second rule condition, which is the important one, in every row, the pivot place is to the right of the pivots places in the rows above. Let's look at a couple examples to understand what I'm actually saying here. So, examples. And let's look at this matrix. Three, 4, 5, 6. Okay. Is this matrix in row echelon form? What do you think?
No.
So what do? We look at the conditions. First of all, does the first condition hold?
Yeah.
Yeah, and this is what you learn in discrete mathematics. And I hope when you learn that false, everything derives from false. I'm not sure how they say it. In Hebrew, it's shekel b'ol kol davar. You learn about the
Vacuous truths.
what?
Vacuous truths, something that's true because it doesn't exist.
Yeah, but did you learn logics in discrete mathematics? You learn about the I don't remember the names, kasharim, the connectors.
Yeah, imply.
Imply, and if the left side of imply is false, then the whole implication is true, right? So that's the case here. I say if there are lines of zero, then, but since there are no lines of zero, then no problem at all. Yeah, I bought some socks at London. And so the first condition holds with no problem. Second, at least I didn't buy donkey milk chocolate. Next, in every row, the pivot place has to be to the right of the pivots above. So what are the pivots in this matrix? So in the first row, what is the pivot? The first element, 1, right? This is the pivot here. And what is the pivot on the second row?
4.
It's 4. And is the pivot 4 is the pivot 4 to the right of the pivots above it? No, it's just underneath it, so it's not an echelon form. And again, I remind you the first intention behind it, the variable x appears both in the first equation and in the second one. We don't wish that to be the case. We wish to cancel it. Okay, so that's not row echelon form. However, if we'll look at the following matrix, ampersand, and 1, 2, 3, and then we'll take the second from the second row 4 times the first, 0, and minus 3, minus 6. Is this? I need to write. It's not an echelon form. Not echelon. What about the second matrix? So the pivot on the first line is 1. What is the pivot on the second line?
3.
It's the minus 3. The pivot is not actually the number, it's the place of the number, right? But it's where minus 3 is written. And is this in echelon form? This is indeed in echelon form. Okay? And next, we have reduced echelon form. If A is in row echelon form, it will be called reduced echelon form if the following two added conditions hold. So when I'm saying A is already row echelon form, we know that if there are lines of 0, they must be on the bottom. The pivots must be to the right of the pivots above them. Now we'll say a bit of Hebrew. This, first of all, I'll explain it in English, but this row echelon form forms a form, I'm using the same verbs, but of steps. It takes the shape of steps. So in Hebrew, it's called medorag, from madrigot. Doesn't really matter, right? But so it's called, it may matter for you in the future because they will say the matriza is medoreget. But in English, it's called row echelon form. I'm not sure even why. But the shape of steps is because we demand the pivots to be to the right, and the idea is that the variable that appeared here will not appear again, and that's why we can calculate this variable according or using the variables to come. That's the idea behind it. And the reduced echelon forms is a better form than this, because it makes sure that, for instance, the y here will appear only in this equation. You won't even need to substitute it back up here to find out what x is equal to. Okay, so I'll write it in this form. And one more thing, this is the coefficient of y, right? So the equation behind this will be minus 3y minus 6z, whatever. It depends in whether this is a constant or a coefficient or a variable. I'll talk about it later. But let's focus on minus 3y. I don't want minus 3y, I want y itself. So what do I wish this coefficient to be? 1. We want the coefficient to be 1. That will be the first claim of reduced form. And the value of the pivots is always 1. And now I'll remind you some properties of a field which we started the course with. If the value is not 1 and it's not 0, can I make it 1? For instance, minus 3, can I make minus 3 to be 1?
Yeah.
I can multiply by the inverse, and that's one of the properties of the field, that you must have an inverse number to any number other than 0. And also, must there be a number which is 1? Yes, 1 and 0 have to be in any field. 1 and 0 are the stars here, because pivots are defined as the first elements which are not 0. And in row echelon forms, we demand that they will equal 1. That actually gives us the solution. And the second condition is every value in a column above a pivot must be 0. Okay, so the zeros and 1 star here. And let's take this matrix, which we worked with until now in the example, and continue with it. So we have this matrix, and if we'll divide the second row by minus 3, we'll get here 1, 2. And I will ask you, is this row echelon form? Well, it is row echelon form. Is this reduced echelon form? So let's make sure. First condition, is the values of both pivots 1? Yes. For start, later you won't need it, but for start, I always mark the pivots and then I look at them and say, is the value of the pivots 1? Yes, there are 2 pivots. Pivot is the first element of the row different than 0. On the first row, it's this element. On the second row, it's this element. They both equal 1. But is every value above a pivot 0? No, this value here is 2. So this is not reduced, and we'll reduce it by taking the 2 times the second element out of the second row, out of the first row, and this will be 0, and this will be -1. And now, is this a reduced form?
Yeah.
So this is reduced. And sometimes students mistake to think it's not reduced because they see here the -1 and the 2, any elements which is not 1 and 0. But the 1 and 0 should be in the pivot columns. Other columns could have any number they like. Okay? Any questions so far? Yes.
Yeah, is this only for matrices that aren't square?
No. It's square I give specifically example of matrices which are not square because that's the less natural notion, right? But all definitions hold true for square matrices as well, of course. Okay, for any matrix of any size. Important note, we used elimination to get from the original matrix to the reduced version. However, this is not the same matrix. I don't know if it's obvious or not, but many students get a mistake because they say we did allowed operations, right? It seems like algebra. We took out 4 times the second row from the first row and we moved from a matrix to a matrix, but it's not the same matrix. A matrix is defined by the values in it. The first matrix is 1, 2, 3, 4, 5, 6. The last matrix has other numbers completely. 1, 0, -1. Okay, so it's not the same matrix. What is the same? Can any of you say? What is the right thing to say about the connection between the last matrix and the first matrix?
They're equivalent.
In which way?
You can get from one to the other performing the same operation.
That's true, but that's not high. But that's not what interests us, right? Currently. What interests us currently? Why do we work with matrix currently? Why did I say currently so many times? Because later, the next chapter of the course, we will study matrices for the sake of matrices, not with any connection to, but I don't want to say the word. What do we use matrices now as a tool to solve a linear system of equations? Later, we will study matrices by itself. For instance, just for you to understand what I'm talking about, there is a matrix whose whole job is to rotate the plane. When you multiply by this matrix, every vector gets rotated. Very important for computer games, right? It has nothing to do with the system of equations, okay? But for now, the first time we pick at matrices, we study a linear sets of equations. So what is the connection between the 2 matrices, the first and the last, with regards to the linear system of equations? they have the same solution. The matching linear systems of equations have the same set of solution. I can't explain enough how important it is. I think most of the confusion is usually in linear algebra 2, but sometimes in linear algebra 1. Sometimes we give the students a matrix to work with and ask them some question about the matrix, and then they use elimination process, even though it has nothing to do with linear system of equations. But sometimes it ruins the entire question. If we do the elimination process, we get entirely different matrix with entirely different answers to the question, right? So you must, and I'll finish with that. You must say it's not the same matrix, it's not the same system, but the solutions are the same. Now, speaking about it, I wish to show you it geometrically as well. Look at the first. Let's look. Let us look at. Why is there an apostrophe there? What's let's?
It's
Let us.
Yeah.
right?
no, there's
it is.
no. There's two types of apostrophes. There's apostrophes for is, and there's apostrophes for multiple people. So if you put the apostrophe after, it's for one person. If you put it before, it's for multiple. It's the Adam
Okay.
system.
Okay.
It's English.
Yeah.
No, bro, I was telling you this. Let us.
Yeah, that's what I
Drop the
thought.
let us.
Yeah, that's what I thought. But usually it's for is, not us. Whatever. Sorry. Let's
It's other
let's
things
look.
like could not, couldn't.
Yeah. Okay. I don't know. Sorry. Let's look at geometric interpretation of the above note. Okay, it's not mandatory, obligatory to look at the geometric interpretation, but I think that many times, or at least for many students, it helps. Okay, so the original system is the intersection of two planes. Okay, should have said it. I keep saying that I should tell you about homogeneous systems, and I keep postponing it, and now I really need to. So I'll write the definition, and then I will get back to the interpretation. Definition: a linear system of equations is called homogeneous if all of the constants Bi are 0. In that case, we do not write the constants column in the matrix. I'll give you an example. If the system of equation is as follows, let's do square root for Thomas. Say it's x plus 2y plus 3z equals 0. 4x plus 5y plus 6z equals 0. 7x plus 8y plus 9z equals 0. So that is called a homogeneous system of equations because the constants here, right, these are called the coefficients. The constants here are all 0, every one of them. It was enough that there will be a 1 here, that it will not be a homogeneous system. But if everyone is 0, then it's homogeneous. And think about it, there is no reason to write it in the matrix because every operation you will do between 0 will always remain 0. So when you have an homogeneous system, the matching matrix, the matrix that describes this system will be matrix 1%, just the coefficient 1, 2, 3, 4, 5, 6, 7, 8, 9. Agreed? So why did I need to mention it now? Because in my head, when I told you that the first system is a plane, I assume there are 3 variables and no constant. What does it mean? That the constant must be 0. Okay, and that's the way I wish to interpret this matrix. And often students ask themselves or ask me, so how do we know if there are 2 variables and 1 constant, or 3 variables and the constant is 0? And the answer is simple. Someone has to tell you. You're not guessing it. If I give you a matrix in an exam and tell you, look at the system equation, the system of equation, I will tell you, look at the homogeneous system of equation that matches the matrix, or the non-homogeneous system of equation matching that matrix. I have to tell you, you don't guess it. Okay? I will give you an example in the following spirit. So, example, and then I'll get back to the geometric one I promised. Looking at the matrix, so the homogeneous system it represents is, how many variables does the homogeneous system have?
3.
3. X plus 2y plus 3z equals 0. 4x plus 5y plus 6z equals 0. The non-homogeneous system is, and it's the same matrix, and it can describe a couple of things. Sometimes students tell me, how can it be that the same matrix both describe this system and this system? And I answer to them, how could the number 2 represent both 2 students and, I don't know, grade 2? Numbers can, algebraic structures can represent different things, right? So in different contexts, it could represent different things, but you must know the context, and I will always tell you. Okay, so I just finished my thought, and I will answer you, Thomas. So the non-homogeneous system, how many variables does it have? 2. And it's x plus 2y. So what is the third number in the row? That's the constant. No, it's 3, it's true, but that's the constant, right? And that's 4x plus 5y equals 6. So the same matrix represents both these systems. Someone has to tell you which system is it talking about currently.
But if we don't know that context, then we can't do it.
Exactly. And and what I told you before, sometimes matrices will not even, we won't look at it. We won't care even about the system they represent, right? We don't have to. A matrix is a table of numbers. It could represent many things. Without context, you don't know what it means exactly. So I will always give you context. Okay, that's just like the number 2 without context is meaningless. You have to say to what, right? Even if someone tells you, I don't know, I weigh 100. 100 watts, right? What I'm trying to get at is that we often need context when dealing with algebra. So here as well. Okay. So I needed to say that at one time, right? I just needed to do it before the geometric interpretation, okay? So I'll get back here and I just write and I'll answer you, Thomas, I didn't forget. Look below for the interpretation. Interpretation of the matrix. Homogeneous to homogeneous system. Yes, Thomas.
Two questions. First, the echelon form is both for homogeneous and non-homogeneous.
Yeah, it doesn't matter. I specifically do the echelon form before, and because, like I said, matrices could even be not relevant to a linear system of equations, but the echelon form will be.
Okay.
Even though I presented it as if it has to do with the system of equations, but later we see it stands by itself.
You can't really go from non-homogeneous to homogeneous and vice versa, right? Matrix.
It's a different system, yeah, no.
Okay.
Okay. So the geometric interpretation. So now I will copy the matrix, and now you can understand what I mean. And the system, the homogeneous system is x plus 2y plus 3z equals 0, 4x plus 5y plus 6z equals 0. These are two planes which I can show you on GeoGebra theoretically. I'll open the online version. I'll reinstall this one later. Start calculator. 3D. So it was x plus 2y plus 3z equals 0. X plus, 4x plus 5y plus 6z equals 0. And I'll change the colors. Purple is nice. Okay, great. So the linear system of equation represent this geometric form shape, and the solutions is the intersection line of the two planes. Agreed? Now I'll cover these two up, and I will wait, first of all, I'll copy the picture. So this is the geometric interpretation. And now I'll go to the system of equations to the matrix after we did the elimination process and we got to the reduced echelon form, which is this. A different system of equation. Geometrically, it will be quite clear. And this matches the homogeneous system. You tell me, what is the first equation?
X minus z equals 0.
Exactly, that's the first equation, right? What is the second equation?
Y plus 2z equals 0.
Equals 0, that's true. And now let's draw these two planes. So I cover these two up, as I said. What was it? X minus z equals 0. Let's even give it a different color. Let's go orangey. And the last one is y plus 2z equals 0. And what do we see here? These are two different planes than the two that came before. I will show you it in a bit. But what do, sure if you see it clearly, to be honest, I'll change color to, yeah, I think this is a bit better. So you have the intersection line is here, right? What will happen if I bring back the other two planes?
It will be the same intersection.
It will be exactly the same intersection. That's the idea. The elimination process did change the question. The first question was the intersection of these two planes. After the elimination process is the intersection of these two planes. But I promised you as a theorem that the set of solutions, meaning the intersection, must remain the same. So I changed the question to an easier one, to one I can solve easily. Okay, and now I'll take a screenshot of these two planes and then all of the planes together on the same shot. Get my point across. You see, altogether these are 4 planes going through the same line. But you should think about them as pairs. The purple and the turquoise were the original pair. After the elimination, we got the brown and the orange and the red. Okay, but each two pairs has the exact same solution. And that's what happened geometrically. Is it important solving a linear system of equation? Not at all, right? But like I said, sometimes it helps to understand what's happening behind the curtain, okay? Or meaning, I don't know, whatever you wish to call it. Okay. So, now another definition. I don't have many more. Well, I do have many more, but for this subject, definition. In a matrix that represents a non-homogeneous system, this is very specific to matrices as when they represent a non-homogeneous system. A row which has a pivot in the last column is called a contradiction. Now, you would say you already knew the word contradiction. You will see a contradiction row. In Hebrew, we say shuat stira. Okay, but what I'm getting at is the contradiction here is actually a contradiction in the system of equation, as you will see in the following example. Let's look at the matrix. Usually when we wish to represent a non-homogeneous system, we put a dashed line there. Not mandatory, but it helps. And look at the following last line. What did I say in the definition? I said that the pivot is in the last column. What does it mean for the equation? All of the coefficients of the variables are 0, So the left-hand side of the equation is 0, but the pivot, the last element in the column of the constants is different than 0. So the equation, and it doesn't matter what the entirety of the matrix is, the last equation is 0 times x plus 0 times y plus 0 times z equals 2, which has no solution. And if one of the equations has no solution, then the entire system has no solution, because solution must solve all of the equations. So if you see a contradiction line, a contradiction row, you know the system have no solution. Okay, agreed? So proposition, which I won't prove, a system of equation has a solution if and only if in its echelon form there is no contradiction row.
I was just reading that the name in English is that the matrix is consistent or inconsistent. Like it's
Yeah, but I want to speak about the row.
the row, yeah.
Whatever. This is one of the names that we won't use a lot. We use the concept, right? If you're solving some kind of exercise, once you see the contradiction row, then you stop. So I don't care how you call it. You won't have to call it. You will just look at this and you will tell me there are no solutions. Hey, there are some names that are important to me. This one doesn't matter. Yes.
I'm sorry I wasn't here earlier in the lesson.
Yeah.
Is the echelon form the same as the reduced?
No, it's a bit less. It has the reduced is a type of an echelon form. Okay, it doesn't really matter, but this is an echelon form. The pivots are to the right. In Hebrew is medoreget. You have the shape of stairs. The reduced echelon form also say this is 1 and above it will be 0. Okay, so it's a better form, but they both represent kind of the same thing.
So above, in reduced, above any pivot will be a
Yeah,
zero.
exactly.
Okay.
That's yeah, every value in a column above a pivot must be 0. Okay. So it's obvious why if there is a contradiction row or the system is inconsistent, there is no solution. What is less obvious, and I will not prove, is why when there is no contradiction row, there must be a solution. It's because we can substitute parameters into the unbounded variables and then find out what the bounded variables equal to. So it's not very interesting. We will see it, I think, when we'll solve exercises, but I don't wish to go into a rigorous proof of it. When I say proposition, it's just the theorem for you. It's just less important. It's a true statement that you can use wherever you like during the course. I don't know, personally. Okay. So another definition. Now I really am nearing the end, I think. A variable is called bounded. תלוי בעברית. It's called bounded if there is a pivot in its column, right? Every column represents the coefficients of one variable. So if there is a pivot in its column in an echelon form of the matrix. Okay, in the original matrix, it has nothing to do with anything, right? Usually the whole column, all of the pivots are in the first column, it doesn't matter. But in the echelon form, a variable which has a pivot in its column is called bounded. The rest of the variables are called free or unbounded, whatever. Free variables, unbounded variables. In Hebrew, it's talui and chofshi. So I use the direct translation of that. Any questions so far? Let's do an example. So let's look at the system of equations we already have and work with it. So we have this system of equations.
Sorry, for there not to be a pivot, it means that it's all zeros, or
For there not to be what?
a pivot in the
Yes, in a row.
in a row,
But
just
But
zeros.
it's per row. It is confusing because the definition of a pivot is by the row, but its location marks something about the column, right?
Mhm.
So there could be a column without a pivot. I will continue to say pivot. And there could be a column without a pivot. Like, you know from where? Who said pivot, pivot, pivot?
Yeah,
Right,
that's from
Ross, yes, pivot. So, so each time I say it, pivot. Okay, sorry. So there could be a column without a pivot, even if there is no row of zeros. Just because no pivot was on this. Are you eating donkey chocolates? It's literally this. It's literally. Okay. It's Barilan. No, it's more disgusting than kosher thing. So I'll give you an example now. I just shamed him. But rightfully so. So the matrix that he disbelieved, right? He looked at it again. Donkey milk, yes, yes, it actually says donkey milk. Okay.
I mean, it would have been worse if I bought it for myself.
Yes. I'm not sure. What does it tell you about your friends? It's going abroad and say, donkey milk, Thomas. Okay. So here the pivots does not matter. Why? Because this is not an echelon form or a reduced echelon form. The pivots are on the start, it doesn't matter. We reduce them, eliminate, do Gauss elimination process. The echelon form we found is, let's take the reduced one because that's what I have ready, is this. And here the pivots mean something. So which variables has pivots in its column? And Thomas, this is for you. Leave the donkey milk for a second, and then you can continue to take pictures. Which columns, which variables has pivots in their columns?
X and Y.
X and Y. So X and Y are bounded, and Z, the third variable, is free. Because in the coefficients of X, there is a pivot. There is a line in which the first element in this column is the first element, which is different than 0, is within this column. In the second column, again, there is a pivot. And it's very confusing because sometimes students look at this and say, wow, we have -1, which is different than 0, and 2, which is different than 0. But no, we look at the column and we look at elements which are the first in its rows, right? This is not the first in the row, which is different than 0. So this is not a pivot. and this is a free variable. And what is the idea behind it? Because the free variables are not the first variables of the equation. The first variable of this equation is x, z is second. The first variable of this equation is y, z is second. That's why z is free, because we can substitute whatever value we wish into z, and then we'll extract x and find out what it equals to, and extract y and find out what it equals to. And because we're in the reduced form, the extraction is simply moving everything to the other side of the equation, because by the definition of the reduced form, every bounded variable appears exactly once, because its coefficient is 1, because there are zeros below it because it's an echelon form. There are zeros above it because it's a reduced echelon form. So every bounded variable appears only once, and you can calculate it using the free variables. Yes.
Can you have an echelon form where the number of rows is larger than the number of columns?
Whatever, yeah. Every size of matrix. Because I think we spoke about it. It's the same as asking, can you find the intersection of 4 planes or 10 planes? Why no? You see what I mean? There is no connection between the number of variables and the number of equations. Okay, equations are some kind of word in English, illuts. What's illuts? You're looking up, please.
Okay, what about
It's constriction. Yes, constriction. Every equation is some kind of constriction. You say, I need this connection between the variables for some reason, right? And the number of constrictions is connected to the problem you're solving, and it could be any number. And the number of variables is the world you work in. So there is no connection between the two. Okay? In high school, it's always the same. 3 variables, 3 equations. Why? Because then you get in certain examples a single solution. Other than that, there is no real reason to think there has to be a connection between the number of constrictions to the number of variables. Constraints. Thank you. What's constraints? What constraints? You're right. That's the word that I was looking for.
what about reduced variable? Not reduced variable, reduced
echelon form.
The reduced form does not change neither the number of rows nor the number of variables, right? The size of the matrix does not change through the whole process. The number of equations and the number of variables is fixed at the start of the question and is never changed.
You can have more rows than columns by having the last column rows be 0. You can have rows that are all zeros.
Yeah, but it's not on the start. In the echelon form, they will be
Yeah.
0 because every pivot, every row has at most 1 pivot. So you can't go, you can't have too many, any column has at most 1 pivot, so you can't have too many pivots if you have many
right.
rows.
So if it's 3 rows and 2 columns, then
Yeah.
in this example would be 1 0 0 1 0 0.
For the echelon form, definitely. Yes,
Then what's
I'll
what's
tell
the
you
point of
this.
having the
Because you don't start with echelon form. That's what I said. You
Okay,
start with
right.
some kind of question. You don't know ahead, but it is true. The following statement is true. If a matrix has more rows than columns, then its echelon form must have rows of zeros. That is definitely true. Okay, because every pivot must be at its own column. And if there are more rows than columns, there cannot be a pivot in every row. Okay? Yes.
I'm a bit confused. Maybe I'm looking forward too much. That in this case, every non-free variable is zero in the row that's not their pivot.
Coefficient, not the variable.
Sorry, the coefficient. Yes.
Yes.
So, is there a connection? Like, does it always happen? Can you make it
Yes,
happen?
yes. That's what I said before. Every variable appears only in one equation. Saying that, I think you misspoke, and that's what I corrected you. When you say the variable is zero, then you think the solution must be zero. No, the coefficient is zero. That means the variable is not even referenced to in this equation. So let's look at the equation system of the reduced form. We did it before. We'll do it again. Where was it? Here. And I think it will answer your question. If not, then ask me again, of course. The system of equations that matches this matrix is this. And then you can do the following. We substitute parameters into the free variables. In this case, only z. So z equals t. Okay, you saw it's a matter of flavor, taste. Here the system does not substitute a parameter, it just calls the variable by the same name x3. I don't like it. Students usually don't like it because when you see x, y, and z, it seems like a question needs solving. When you see t, it looks like a number that was solved. So we always substitute some parameter into the variable, even though it is kind of a meaningless gesture. But then after it, what does x equals to? Simply t, right? What z, but it's t. And y, when then find the values of the bounded variables, x equals t, y equals minus 2t. Right? You see why? And that's the idea behind it. That's what we always do. We find the free variables, we substitute parameters into them, and then we find what the bounded variables are equal to. That's the whole point of the reduced echelon form. And now we can say so the general form of the solution is t minus 2t t. Yeah. You can go back to GeoGebra and I could write I take t out to the common factor and I get 1 minus 2. I'll do it as a vector, sorry, vector. 1 minus 2, 1. And you see that this vector is really the vector that creates the line, which is the solution to the system. Okay, we actually found the solution to the system. Any questions so far? Yes, Thomas.
Yeah, so what I was getting at is that the echelon form
Yeah.
doesn't mean that after the pivot, everything is zero except the free variables.
No, in the row,
Not in the row, right?
just in the column.
Yes.
Because I don't say I don't wish to see other variables that come after me. when I look at my column and say, I am a bounded variable, I wish not to appear in any other equation. But the free variables can appear in all equations. That's what you see in this case.
Yeah, I'm just saying, like, it would still be the echelon form if you had like 1, 2, -1, and
It will be echelon, but not reduced echelon. That was exactly the difference. In the reduced echelon, wasn't yeah. In the reduced echelon, look, every value in a column above the pivot must be 0. In the echelon, it's not required.
okay.
And if it's because you're studying from other places, they teach you to go to the row form, find the last variable, and then substitute up. I don't like it. I think it's a recipe for mistakes, and it's not what I would do programming a computer to find the solution. I would go to the reduced echelon form. It's also unique, and then from it you get the solution like that. Okay, and I just before the break, I will give you another statement and that is connected to what I just said. Note, if we wish to know how many solutions the system has, we use echelon form. If we wish to find out what are the solutions, to actually find the solutions, not just how many there are, we use the reduced form. Okay, why? Because what would tell you how many solutions there are, that will be whether there is a contradiction row and whether there are free variables. If there is a contradiction row, then we have 0 solutions. If there is no contradiction row and we have free variables, then we have infinite number of solutions, because in the free variables we can substitute any number of the field if the field is infinite. And so just knowing how many solutions, it is enough to go to the echelon form. But if you wish to find the general solution, like I did just now, the easiest and best way to do it is go to the reduced form. Okay, and so let's take a 15 minutes break. from London, and I slept for almost 24 hours straight. And I don't think it was jet lag. Okay. So, I'll give you a summation of what do we do when given a linear system of equations. You do the following steps. One, use Gauss elimination to get to an echelon form of the matrix. From here, you can know if there is a contradiction rho, there are no solutions. I'll change it up a bit. Sorry. Okay, it will be step 2. 3. If there is no contradiction rho and there is at least one free variable, then there are infinite solutions. If there is no contradiction and all of the variables are bounded, I could say there is no free variable, it's the same. So how many solutions do you think we have in this case? Then there is a unique solution. We'll do a few examples right after the summation. This is actually, you know that you need to use algebra to solve almost any exercises, any form of mathematics other than discrete mathematics. So the same goes for matrices and linear algebra. In order to solve any exercises, you need to be very, very fluent in what I'm describing here in this algorithm. This is like a major step. It's a question on the test. The ability to do what I say here is very, very important. That's why I will give you a few examples in a bit. I'll just finish it up first. And 5, in order to find the set of solutions, we find the reduced form, substitute parameter into the free variables and calculate the bounded variables. So these are, I don't know if it's really 5 steps. Most of them, if you notice, is step 1. This is most of the work. It's finding the echelon form, and the rest is simply understanding what you're doing. Yes, Thomas. The donkey. Regurgitate. Yes.
Did we describe how to find free variables?
Yes. We said that bounded variables, and I specifically talked about it with you, The bounded variables are the variables which has a pivot in their column. All of the rest are the free. Okay, so yes, you go to the reduced form, you mark the pivots, and then you say if there is a pivot in my column, I'm a bounded variable. If there is no pivot in my column, I'm a free variable. Okay, that's why I say most of the action is step one. The rest is simply understanding what the echelon form teaches me. Any other questions? Let's do an example. Example. So let's look. I think I have it written. And I'll just copy it here. Let's look at the following system of equations. Geometrically, and I won't use GeoGebra anymore today, I think, but geometrically, it's the intersection of three planes. What do you suppose the intersection of three planes would be?
Either a dot or nothing.
So that is a false answer, but makes sense because every constraint lowers the dimension, so-called. It's simply not true, the last statement I did, but that's what you think about. Say one plane, then you take the second plane, the intersection now is a line, right? And when you take the third plane, it will be a dot, a unique solution, right? However, I will do GeoGebra. However,
Except if one is dependent on the other, no?
but what does it mean dependent? We still didn't learn the concept of dependent. But let's take, and I have it ready here, so I'll do it. And the first two planes are the planes I wrote, and the last one is 7x plus 8y plus 9z equals 0. That is the last plane. I will change its color. And you can see what is the intersection of these three planes? It's
A line?
It's a line because they all pass, not pass, they all go through the same line. Trying to find a good angle. They're quite close to one another. Yeah, I think this is fine. Okay, so that's what happens. And again, I say you don't need the geometric interpretation because I keep saying it because students might worry and say, I wouldn't know how to graph this during test. Obviously, the whole thing that I'm trying to impart on you is the beautiful thing about algebra is that geometrically we can see what's going on, but to know that that is what's going on, it is so easy algebraically. Just by doing Gauss elimination on the matrix, I will find out that the intersection is aligned without the geometric drawing graph. We'll see it in a second, okay?
Okay, yes.
But that's what I said. That's why I don't like when students make connection between the number of equations and the number of variables. Here there are three equations, but they're actually a line of solution because they all go through the same line. That's what happened in this specific example. That's why I always use it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and it's nice. So now we will find out that this is the graph basically, but only using algebra and only using these 5 steps. And the first, the main one, is using Gauss elimination. And I remind you, this is a homogeneous system. all the constants are zero, so I don't write them in the matrix. So I just take the coefficient matrix, also copy paste this, and I will use Gauss elimination to get to the echelon form. So how do I get, yes, Thomas?
What I was thinking is do the third row minus the first row. And
No. Why? It's not it's false, but I wish to teach you the main thing, main way you need to think about it, the way a computer would think about it. And after you control that, you can try to do some shortcuts. But the main thing is, this is a pivot. Below it, we want zeros. That's what we do. We cancel out these values using the first one. And then we'll go to the next column and do the same. This will be a pivot. And we cancel this element by this and so forth. That is the Gauss elimination process. Sometimes there are shortcuts that help us do less operation. But from my experience, usually going the straight way is the fastest one. And students that look for shortcuts usually get find themselves chasing their own tails. So I suggest, at least for the start, cancel out the first column, then the second column, then the third column, and so forth. Okay? And what would we have done if this was zero here?
we would have reordered the.
Yeah, we move a row which does not have zero to be the first and cancel everyone by it. And why can we always cancel? Because it's filled. We can make everything one if it's not zero, and we can cancel. So what I suggest you do here, what's the natural thing to do here, is row 2 minus 4 times row 1. Okay, do you see why? Because this will cancel out these 4, and that's my entire wish now. Okay. And also afterwards, I'll do 2 steps in one. What will be the next step?
Do the third row minus.
R3 minus 7 times R1. And here sometimes you can do things like cancel out from the 7 using the 4. Here obviously it's not a good idea because you'll get fraction and it's not fun. Usually you wish to do the 1, but here sometimes shortcuts are okay, I think. If there was, for instance, 4 and 4 here, I might be tempted to cancel out these 4 by this one and this 4 by the 1. So that sometimes can help, but still cancel out the first column. That's the main thing. That's what you should do. Okay. So what do we get? We get a different matrix, like I said, but the set of solutions remains the same. So now we have 0, 5 minus 8 is minus 3, 6 minus 12 is minus 6. Now here, 7 minus 7 is 0. 8 minus 14 is minus 6. 9 minus 21 is minus 12. And I'm not doing it that fast, but if you listen to me before, I always use this metric, so I remember it by heart. And what would be the next step now?
R3 minus R2 times 2.
Yeah, 2 times R2, exactly. And why? We wish to cancel out this number. Okay, to get to the echelon form, the shape of staircase. So here we get 0, and here we get 0. This basically means, geometrically, that the intersection of three planes can be described by the intersection of two planes. One of them is not needed. So, is this row echelon form? The answer is yes. Why? The zero row is on the bottom. The pivots are 1 and minus 3. And each pivot is to the right, to the ones above it. So this is an echelon form. Is it a reduced echelon form? No. So what good is it? That's the end of step 1. It tells me how many solutions do I have. Step 2 is irrelevant because the contradiction row will only appear in a non-homogeneous system. There couldn't be a contradiction row here. Step 2, are there, step 2 and 4, 3 and 4, sorry, are together. Which variables are bounded and which variables are free? And that is due to the pivots. So is there a pivot in the first column? Is there a pivot in the second column? Is there a pivot in the third column? No. So since there are pivots in the first two columns, X and Y are bounded, and Z is free. So there are infinite solutions. Okay. So if we wish to find a solution, we will go to the reduced form. Next slide. In order to find the general solution, we need to get to the reduced form. Okay, I'm not doing it here because I did the same example just 2 minutes ago. These two rows were before without the zeros. Let's do another example.
Can you go for a second to the description you gave for the third step?
Yes. If there is no contradiction row, that's the case, and there is at least one free variable. Z is the one free variable. Really?
Yeah, no, I'm just thinking that for these to work, like you chose a square matrix on purpose, or no, I know what I mean is, you the sign said as a free variable because there was no a pivot on its row,
On its column.
right?
Not because of the row. That's why I keep
I mean-
saying it's not because of the row, it's because of the column.
Yeah, that's right. Just because there would be one row that would have the pivot if in the reduced form. But
Because it's square, then there is a connection between the zero row and the pivots. But for matrices which are not square rectangle matrices, it's not true. And in any case, looking at the zero row is irrelevant. So I teach students not to look at it because it's always confusing. Then I put in the test a rectangle matrix and everyone loses their mind, like the Joker said. But if you're looking at the columns and the pivots, it's you cannot fail. So it's much better. Okay, so let's look at another example. So now I'll just I'll write the matrix straight ahead. X, Y, F constants. So this is also a square matrix, to be honest. But now I'm looking at the non-homogeneous system. And that would be 1, 2, 3. And now let's do something different. -1, 3. And 0, 1. And 2, 2, 8. We're stepping it up a notch. And I will ask for every value of A, find out how many solutions does is the non-homogeneous system have has Okay, it's the first question with parameter. That is what I actually asked in the test always. But that's kind of simple because the parameter just appears at the end. It's a bit harder when the parameter is in the middle and when there are 2 parameters or 3, and and we'll do a few examples to be very fluent in this kind of solving these kind of questions, because it's so important throughout. I mean, including linear algebra 2. In linear algebra 2, and it's the parameters in the matrix are naturally occurring when you're looking for eigenvalues, and you need this ability to work with them and know what is allowed, what's disallowed, what is recommended. So this is the first such example, but there will be more. Yes.
Is there a different geometric interpretation of non-homogeneous matrices?
It's not different, it's the same. Geometrically, it's the same, to be honest. Like equal 0 is just a very important case where the plane go through the axis point, right? And in a non-homogeneous equation, 0, 0 is not a solution. So that's the entire geometric difference between the two. But algebraically, there is simply no difference whatsoever. That's why it doesn't really matter. Geometrically here, by the way, because we have 2 variables, we're in a plane, we're in the XY plane, and each equation represents a line. So this is the intersection of 3 lines. So they might have a unique solution if all the 3 lines go through the same point. They might have infinite solution if all the lines are actually the same line. Obviously, this is not the case here, but in general. And there might be no solution if the 3 lines do not pass through the same point. And I always say I won't use the GeoGebra again, and then I do, and I will. So let's look at how it looks. And first I write A, put some parameter in which I can then change, and I will draw the lines. What are the lines? X plus 2y equals 3. X plus 2y equals 3. That's one line. The second is minus x equals 1. Minus x equals 1. The second line. Now think about the third. First of all, you see that there will not be more than one solution. Okay, geometrically, algebraically, like I said, we just eliminate the matrix, go to the echelon form, and we find out. But geometrically, the line could pass through these points or not, and it depends on A. So the next line is 2x plus 2y equals A. And now I can change A. Here you see, and oh, what do we see here? Can you read the value of A? It's here on the screen. It's 2. It's 2. And that's just from the geometric interpretation. We see using the software that when A equals 2, then the equation does have a solution. But when A is not 2, it does not have a solution. There is no common intersection to all 3 lines. Agreed? So that's the idea behind the, it's not idea. That's the geometric interpretation of what we're doing. But again and again, the algebraic thing is the same. And the nice thing, it's the same in every dimension, right? Higher than 3 dimension, we cannot imagine what it looks like, but it doesn't even matter. We simply reduce the metrics. So let's do it. I'm just right, sorry, this, I know what I should have done. I should have taken the screenshot with A to know what its value.
You can take it when A is 2 to know.
I'll do it. I agree. I'll check both cases. A equals 2. Yeah. Now we wish to see that using the elimination process, we get to the same result. And through the, I don't know, I think using the software is the closest thing the mathematicians have to experiments. So using the experiment. Let's do the algorithm. So, first thing, we wish to cancel the first column. So our first 2 operations will be R1 plus R2 plus R1. And the second operation is R3 minus 2 times R1. And then we find it. And that's 0, 2, 4. This 2 minus 2 is 0, 2 minus 4 is minus 2, A minus 6. Agreed so far? What would be the next step?
Dividing the second row by 2.
No, that's on the next step. Canceling out. Dividing is when you go to the reduced one. Or you need to cancel out, but here is so easy to cancel. This is minus 2, this is 2. The next step is to cancel out this minus 2 to get to the actual form. So R3 plus R2. And we get to the following matrix. It's different matrix, but the system has the same solution, the same set of solution. So you get 0, and here you get A minus 2. First of all, you see, we find algebraically, we're not sure yet, I will tell you in a second, but we see A and 2, and it looks good. So now, what do you think we should say? I'll ask you it differently. What are the pivots of this matrix? In the first row, what is the pivot? 1, right? In the second row, what is the pivot? The 2. What about the third row?
The only if
the correct answer is that we're not sure, because the pivot is the first element different than 0, and we are not sure if A minus 2 is 0 or not. That's the main secret for this kind of question. We are not sure what is the pivot of the last row, since we don't know if whether a minus 2 is 0 or not. So we check all cases and we say if a equals 2, meaning that it's 0, I think maybe it's easier to start with if a is not 2,
There's a contradiction.
yeah, then there is a contradiction and no solutions. So for every a other than 2, there are no solutions. And if you remember what happened just a few moments ago in the GeoGebra, that's exactly what we saw in our experiment. When a was different than 2, there was no solution to the system. There is no common solution to all 3 equations. However, when a equals 2, if a equals 2, we plug it in. And what it is, it keeps making me jump each week. So this is the matrix. It is in echelon form. The 0 row is at the bottom, and the pivots are on the stairs, right? Is it a reduced echelon form? No. So I'm saying this is in echelon form with no contradiction. And what is the next question we should ask ourselves? Look at the algorithm, right? So, like I said, 1 is the bell of the ball. It's the main thing. It was hard for us to even Gauss eliminate because we were not sure what are the pivots, but we did it. Now we have an echelon form. Next time I'm checking whether there is a contradiction. There is no. What is the next thing we should check? Step 3 and 4.
To have a free variable or not.
Yes. So how do we do it? We look at each variable, at each column, and ask ourselves, is there a pivot in this column? So the column of X, is there a pivot in the column of X?
Yes.
Yes. Is there a pivot in the column of Y? These are all the variables we have. Okay. Both variables are bounded, and therefore, what is the conclusion?
There's no free variable.
How many solutions? There is a unique solution. And again, in our experiments, that's exactly what we found out. If we wish to find said solution, what do we need to do?
To reduce form.
And we need to go to find the reduced form, right? The echelon forms tell us how many solutions there are. The reduced form tells us what are the solutions. So we'll continue and go to the reduced form in this case. So what would be the next step to go to the reduced form? Now we will divide by 2 in order to make the coefficient of the pivot 1. So now we'll have 1 and this is 2. Is this a reduced form?
Still no.
So what will be the next step?
R1 minus R2 times 2.
Yeah, we need to now think about it. When you go to the echelon form, you cancel out below the so-called diagonal. It's not diagonal, it's the staircase. right? You cancel out below the stairs. And when you go to the reduced form, you cancel out above the stairs. So we need to cancel the 2 there. So we go R1 minus 2 times R2. And then you get 2 and 0 minus 1. No, yes, that's one. This is the reduced form. And what are the equations? Therefore, x equals minus 1. Y equals 2. The solution, and the solution is the point minus 1, 2. It's unique. There is no free variable. There is no parameter. Each bounded variable is fixed for a number, and that's supposedly the intersection. Let's make sure it is. It looks fine, and I'll write it anyway. Indeed. Okay. So we figure out the whole story not using GeoGebra, by using the process of elimination. And any question so far? And before I continue to the next example, I wish to give you a place to try some of these yourselves. I have many different courses in which I give such a question, and I'm trying to think of where there will be the largest Magal. Okay. Sheva, no, that's I'll go to another course and think this is better. Oh, this one. Yeah, I think that's yeah, that's much better. Okay, so I'll give you a link first of all. In the following link, you can solve question number 1. You can and should. Okay, so and I'll give you the link and I'll show you. It's in Hebrew, but I think even the English speaking guys will be fine with it. And let's look at an example. The first one, sorry. First one is not a test, it's a collection of many questions with solutions. There are such questions here as well, but you can skip it, I think. The tests, however, look at question 1. It says, let's look at the following system of equations with the variable x, y, and z and the parameter a in the real field of real numbers. This is the system, and then I say, and it's the first, it's always the same question. Find for every value of a if the solution has a unique solution, the system has a unique solution, infinite solutions, or no solutions at all. So each one of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, start with the same kind of question. Okay, just different system each time. And almost all of them, just one I think no, has solutions as well. Go here and look at the solution just like I solved with you right now. Okay, so again, I implore you do this. Okay, to make sure you're with me in the material. It's the first, I think, very technical things you must know. Until now, there was a lot of theory, and you might not be sure if you understand anything at all, or be sure that you don't understand nothing at all. But in any case, this is something you can work at, become better, and it's super important. First of all, I will give you on the final exam such a question. That's one thing, but more than that, we will continue to use it all through when we learn about dimension and the basis, the way to calculate these things will almost always involve taking some metrics and finding the general solution to the equation. Not only, but it will happen time and time again. So get familiar with this. And now I'll continue to another example. And find how many solutions does the following system have for each value of A. X, Y, Z constants. Okay, and the matrix is 1, 1, A dash 1, 1, A, 1, 0. A, 1, 1, 8. So this is the system geometrically. These are three planes. I hope to stand by my word this time and not draw it in GeoGebra and just solve it algebraic. So what do we do? What is step 1?
We go to the
In general,
extra.
Gauss elimination. That's the first thing we do. Use Gauss and use Gauss. Less horrible than this squeaking. And it's reminds me of the Nazgul. So first step, use Gauss elimination. And we'll see now the A comes in the first column, not in the last, and we will see what can we do with it. So first step is fine in the sense that R2 minus R1. Agreed? I wish to cancel out the first column. So I wish to cancel out this and this. Now this makes me scared a bit because of the A. What should be the next step?
R3 minus R1A.
Minus A times R1. And now, is there a problem when A equals 0? The answer is no, there is no problem. Why? Because if A equals 0, then we simply did nothing, and that's okay. Okay, so these are the kind of operations you wish to do. What you don't like to do is divide by A, because then you're in a problem. And many students start with dividing by A because they are scared of the A and say, if we divide it, it's 1, then it will be easier. And they actually, first of all, doing a mistake. But even if they check cases, different cases, split to different cases, whether A is 0 or not, they are duplicating the work because they could have handled this A in one step instead of splitting into two branches. Each of them, they have to follow through now, right? And they will also have 1 over A. So these kind of steps, one row minus or plus something times another row, are the best steps. As long as you can keep it, do it. Usually we can go almost always with these kind of steps almost to the end, to the part like it looks like an echelon form, but we are not actually sure because we don't know if it's a pivot or not. Okay, and then we split two cases. Okay. So what do we get here? And you will see it in all 13 examples I gave you a link to before. So R2 minus R1, 1 minus 1, 0. A minus 1, say minus 1, 1 minus A, it's 1 minus A, and 0 minus 1. R3, third row, minus R1, minus R3 minus A times R1. So A minus A, 0. 1 minus A. 1 minus what?
A squared.
A squared. Exactly. And A minus A is again 0. What would be the next step?
In theory, trying to cancel out.
Yes, so now again, it's a bit scary, but we need to hold on tight. We wish to cancel out this, right? So sometimes we say, because this is not 1, it's a problem, we wish to divide by A minus 1 and split two cases. But here we don't need to, because this is exactly the minus of this. All we need to do is sum up the two rows. These are the cases where sometimes you may have to divide, but usually you don't. There are many tricks and so R3 plus R2, we add the second row to the third one. And here we get 0. And here we get we sum them up, so we get minus A squared minus A plus 2, and here we get minus 1.
No, isn't it C plus 0? Because you have a 1 minus A and you do minus.
At which place? Here?
Yeah, because you're not doing.
Added them. I didn't subtract. Right? I added the two lines. Okay, two rows. Okay, so now this is the point where it looks like stairs. It looks like an echelon form, but it's not actually, because we are not sure what are the pivots. Okay, so we wish to know if A minus 1 is a pivot, and therefore pivot, and whether A minus A squared minus A plus 2 is equals to 0. So let's solve this. This is A squared plus A minus 2 equals 0. A1, 2 is minus 1 plus minus square root of 1 plus 8 over 2, which is minus 1 minus 3 is minus 4, it's minus 2, and minus 1 plus 3 is 1. Okay, so altogether.
Sorry, how did you get to A squared plus A minus 2? You did times
Minus.
Yeah,
I skipped a step.
Yeah, but the solution is -1, no? The
Oh, so my solution.
no. I mean the constant is -1.
What? It doesn't have anything to do with the
It
constant.
doesn't matter.
No, I'm just asking myself now, what are the pivots? So this is the first element of the row that might be different than 0. If it is 0, then obviously we're going to have a problem here, right? Because we'll get a contradiction. But if it's not 0, then this is a pivot. Okay? So we need to check what happens. And now I can say that if A is different than 1 and -2, if A is not 1 and not -2, then this is an echelon form, and I will copy it and mark the pivots. Because this is different than 0 in this case. And this is different than 0 in this case. Agreed? And forgot the first obvious pivot. Okay. So this is an echelon form if A is not 1 or -2. If it is 1 or -2, we'll deal with that. Oh, it's easy to see what the answer is, but I will deal with it in a second. So what does that tell us? This is an echelon form, sorry. There is no contradiction, row, right? What about the variables? Is there a free variable or not? No, they are all bounded. Why? In the column of X, you have a pivot. In the column of Y, you have a pivot. And in the column of Z, you have a pivot. Okay, so I write this is an echelon form. I wrote it above, but I wish to brainwash you. This is an echelon form, no contradiction. All variables bounded. And what does that mean? How many solutions? A unique solution. Exactly. Okay. And now we plug in 1 and -2. I will deal with both of them together because if A equals 1 or A equals -2, the third row is contradiction. And there are no solutions.
Solutions with you.
Oh, here, right. Ah, did twice. Why? Because whether A is 1 or 2, actually I don't, to be honest, both of these lines are contradiction. I didn't notice it before because I don't have to. I just noticed this is 0, 0, 0, -1. That's a contradiction. Okay, sometimes the A stays here, and actually it's not a mistake, it's accident, and that A did not remain there because when I gave you the example, this part is the one I always use, and here I just chose random things, and it so happens that the A cancels out and doesn't remain there. But if it did remain there, then sometimes what happens is that say this was A -1. So if A was 1, this whole row would cancel out, and then we can continue. Specifically, it wouldn't help because of the second row, but that's changes from exercise to exercise, but that doesn't matter to us because the process is such that a computer can do it. Any questions so far? So again, I ask you for next week, go to this link verification. And skip the first link here that doesn't matter. And solve questions 1 from all of these. You probably can solve the second 2 parts of the questions, but at least the one I expect you to be able to do is the first one. That's definitely, but you can try the other ones as well. And you can also tell me if there is a problem and we need to go over it. You're a small class. I wish everyone will, as much as I can, be on the same level. So for next week, please solve these kind of questions. And if you find it hard or you're not able to solve, then come and tell me. Tell me on the next you don't come to my home. Okay, thank you, and see most of you guys in half an hour.